all. By the time that you are watching this video, you will have already taken your concept check. Make sure you have put that in your folder. And then I'm going to give you a lesson on the combined gas law. This lesson will go along with some notes in your packet. You can start on page 11 and then we'll work our way through page 14. Your homework for the weekend will be to get through page 16. These are a bunch of practice problems for the combined gas law. And there will be a concept check on Tuesday when I see you. So what are gas laws? Up until this point, we have been focused in on all the different states of matter. So we've been talking about solids and liquids and how they change between them. And now we're going to focus in onto just talking about gases for the rest of this unit. And the reason is that gases behave differently or have some unique properties to them. This was first observed in the 17th century. And this was when they started to discover that unless you knew what pressure and what temperature and how actually amount of matter you had, you could not accurately measure the volume of a gas. And so because of this, scientists started to think about that we needed to have some more parameters to actually know about the amount of matter that you are dealing with when you deal with gases. And this is because they can change both their volume and their shape. And so the things that are going to come up a lot this unit are going to be pressure and temperature. So pressure is how often are those molecules hitting the sides of a container. And we measure that in a lot of different units. In general, the three main units that we're going to use, and there are more than these, but the three main units you're going to see in this unit are going to be atmospheres, millimeters of mercury, and kilopascals. And you can convert between these three units by using their equivalent. So one atmosphere is 760 millimeters of mercury, which is 101.3 kilopascals. The other thing that's going to come into this a lot is going to be temperature. And in temperature, you are thinking of how much average kinetic energy. And so we got a taste of Kelvin last unit, but really it starts to become pretty important because in Kelvin, as we talked about last unit, at 0 degrees Kelvin, you cease to have molecular movement. And so therefore, it is a direct relationship in Kelvin to the amount of motion and the amount of energy you have, which is important. If you ever see STP, we're talking about standard temperature and pressure. And so the values that you see on the screen are standard values, where 273 would be standard temperature. And then any of those pressure values would be standard pressure. They would just be matching whatever unit you're using in the problem or the data you've collected. So we're going to watch a short little experiment. I'd be doing this in class if I was there, but about what is happening in the scenario. So we're going to watch, you're going to make some observations, and then we're going to talk about it. So there's this little marshmallow man. He's getting put into a vacuum chamber, and the vacuum gets turned on. And so actively, air is being sucked out of the vacuum. And then when air is let back in, you get a little squished marshmallow man. So take a second and write down some observations. So what was the initial thoughts? What did you see during the demo? And then what was the final result? So this demonstration really is going to hone in on our first kind of idea of relationship between two variables. And these variables are going to be pressure and volume. And so when the pressure, the atmospheric pressure of the gas was decreased by sucking air out of the vacuum, so there wasn't as much atmospheric pressure inside the bell jar, the volume of the gas was able to expand. Okay, so pressure and volume are inversely related. And then and I don't know if you noticed this, but it got expanded to a point, and then the marshmallow almost kind of went, right? And that was the actual like air pocket bubbles in the marshmallow itself being popped and gas escaping those air bubbles. Okay. This is then why, as the vacuum, if the longer you left that vacuum on, it's actually sucking air out of the marshmallow itself. This is then why, when you increased the pressure back to atmospheric pressure, the marshmallow shrunk to smaller than its original size. Okay. So as atmospheric pressure increases, or as the surrounding pressure increases, the volume that gas can occupy decreases. Okay, at a constant temperature. So at a constant state of motion. This is called Boyle's law. And this inverse relationship was first observed by Boyle, which is why it's called Boyle's law. And it can actually be a calculation. So if we know the pressure and volume of a gas in this scenario, and then we change something, like if we have pressure and volume of a gas, and then we're like, okay, and now I'm going to shove that pressure or that gas into a much smaller container. How is the pressure going to relate? That is then what this is talking about, is how are we going to know the fourth variable? I think of this a lot as if our entire class stood up and started moving around. If we were in the gym, we would not bump into each other or the walls very often. So the pressure we were exerting on the container would be pretty low. However, if we took the same number of kids, the same amount of our class, and we shoved us into a closet and we asked each other to move at the same rate, we would bump into each other more and we would bump into the walls more. And therefore, we would exert a bigger pressure. And so if I take the same sample of gas moving at the same rate and I put it into a different container, larger or smaller, the amount of pressure it's going to exert is going to change based on that volume. And it's that inverse relationship. So these are going to be math problems. It is most important to make sure your units are matching between your ones and twos. So it's like, well, two things. One, it's really important to make sure you're identifying and pairing things correctly. And then it's important that you have matching units. So this one says a sample of gas has a volume of 3.5 liters at a pressure of 760.5 millimeters of mercury. What will the volume of the gas be if the pressure is reduced to 452 millimeters of mercury? And so those first two values, the 3.5 liters and the 765 millimeters of mercury, are like scenario one of your gas, and they go together. That's pressure one and volume one. And then it's like, hey, I took this and now I'm going to put it under a lot more pressure. What would you expect the volume to be? Are you going to expect it to be higher, or are you going to expect it to be lower? And so if you think about that inverse relationship without even doing the math, you're going to expect that the volume of that gas is bigger because the actual pressure exerted on the container went down. And so this gas has more space to move. It is not hitting the walls of the container as often. And so you can set this up mathematically, putting your X in at 4V2 and solving, and you would see that your volume, in fact, is bigger, right? It's not quite twice as big, but it's bigger. And so this is what you would anticipate, and you would be able to double check yourself, because based on the relationship of the variables, this is what makes sense. So take a second and see if you can get the answer to this one. You can pause the video here. Did you get it? 8.2 liters. So we have a 12.3 liter sample of gas at 40 millimeters of mercury. What's going to happen if the pressure was increased? So if I'm going up in pressure, that means that my volume went down because the particles of the gas are hitting the walls of the container more. So now we're going to move on to the next demonstration. And the next demonstration is going to look at two other variables of gas laws. So watch. So there's just a little bit of water in the bottom of a flask. And this is just so that we can kind of visually see what temperature we are getting gas to move. So you bring this gas to a boil, and then you're going to shove a balloon into the container. So now you're taking a container and you're making a sealed system. And you can see pretty quickly that this hot gas is expanding. But then if you take that flask and then you cool it down, It's interesting to see what happens. As that gas cools, the volume it occupies becomes smaller. So much so that now the atmospheric pressure and the atmospheric gas has a higher pressure than inside the flask. And so you actually reinflate the balloon into the flask itself. So take a second and fill out that little blurb on page, I don't even know what page 12. That's describing what it happens, and draw yourself some pictures. So this balloon in the flask or prairie dog demonstration is an example of how volume and temperature of a gas are related. And I personally have a very vivid memory of this relationship, and that I normally tell to my students, but I'm not there, so I'm going to tell it to you. But if you can imagine back with me, Beckett and Ainsley are, Beckett is 2, Ainsley is a baby, and she's in a car seat, and he is in a grocery cart, and I'm walking through the grocery store trying to get dinner one night. And it is back when we had that really, really cold year where there was like -13 outside. Okay. And I am walking through the grocery store. I am trying to get some dinner. I'm a little frazzled. And Beckett just wants a Mylar balloon, one of those big, shiny Bronco balloons. And I'm like, fine, whatever, buy it. And we buy it, and he's all happy and everything like that. And we go get in the car, and we walk through the like gas door of a grocery store. Can you picture that? Like the big open doors, and how they blow air so that the inside stays warm and the outside stays cold, and they can still have like an open door. And we walk through, and this balloon goes from like flying in the sky, and he's so happy, and it just crashes into his lap. And I think it's like the coolest example of chemistry ever. I think it's like the coolest thing because it was such an example of this. The gas in that balloon got so cold that it condensed, and it occupied such a small space that gas then wasn't able to fill the balloon, and it fell into his lap. He did not think this was cool. He begins to freak out, and he's crying and he's kicking and screaming and all this kind of stuff. I'm like trying to get him in the car because I'm like, get in the car because I'm going to be magic. Like, mommy's going to be magic. Just give me a second. And so I get him in the car, and I turn on the heater, and lo and behold, this balloon comes back to life, and I get to watch him realize why this balloon is coming back to life. And it's as that gas heated up in the warm car, it began to expand to fit where it was originally contained. And so this direct relationship between volume and temperature of a gas is as such, right? If you heat a gas up, it's going to move faster, and it's going to push at its container. And if its container is flexible, it's going to expand, right? And then if you cool that gas down, it's going to occupy less space because it's going to move and hit against the walls of its container less. So this was first kind of talked about in Charles' law. Charles was the guy who talked about it. And this is that relationship. If I heat it up and I can push against the walls of my container, if my pressure is constant, then I'm going to push the actual volume of the space that I'm occupying away from me. And then if it is the opposite, then if I am cooled, I'm going to push against the walls of my container less and occupy less space. So this is also math, okay? It is important to know that your temperatures should always be in Kelvin for these problems. And then again, you just need to pair it correctly. So this says a sample of gas is heated from 124 Kelvin to 185 Kelvin. At 185 Kelvin, the gas has a volume of 0.743 liters. What was the initial volume of the gas? Well, if my temperature increased, then I would expect that my initial volume was less than my final volume. And I would set this up like this. And I know it's hard to see, but these are on top of each other. I would have X divided by 124 is equal to 0.743 over 185. And the way you mathematically solve this is that cross multiplication. So you're going to cross multiply and divide, and you're going to end up with 0.498 liters, which is smaller, right? Which is what we would expect. So now take a second, pause the video, and see if you can get this one. Do know that you need to convert your Celsius to Kelvin, and that's plus 273. Did you get it? 285? That should make sense to you because in the beginning, you have 20 liters of air and then it goes down. So the temperature should go down as well. All right, we're almost there. We've got 2 more demos. So this is on page 13. Watch what happens with this demonstration.
Bearded Science Guy here, and today I'm going to show you how to push an egg into a bottle using atmospheric pressure. Start with a bottle that has an opening just smaller than the size of your egg, and then boil 3 tablespoons of water until steam is pouring out the top. Remove the bottle from heat and place a hard-boiled egg at the opening. To speed up the reaction, you can also place the bottle in cool water. The air on the outside will slowly push the egg into the bottle. Normally, if you were to place this egg, Bearded Science Guy here, and
Okay, so what happened? Okay, take a second, look at and write around on your paper about some observations that you just made. What we are noticing and what you have to understand of like the difference between this one and the one prior is the prairie dog had a flexible container. And so you could see the volume of the gas changing based on the temperature. And this was because the pressure was kept constant because of that flexible container. The difference now with this one is that it's not a flexible container. You have a glass flask, right? And you're putting something at the top that's flexible, but it's sealing the container. And so what happens then is that as that gas cools down, we know it's going to occupy less space. And the consequence of that is when your container is not flexible, it's going to hit the walls of the container less. And so that internal pressure is going to go down. It's going to go down so much that the inside of the flask, the pressure inside of the flask is going to be less than the pressure outside the flask. And that atmospheric pressure is going to push on the egg because pressure doesn't like to not be equal. Things always move from a region of high pressure to a region of low pressure. And so it's going to push on that egg until eventually that egg went into the flask. This demonstrates this idea of in an inflexible container, the higher the temperature, the more that those particles are going to hit against the walls of the container because they're moving faster, and therefore they're going to increase in pressure. This is a direct relationship. This was first discovered and first talked about by a guy named Gay-Lussac, and he stated this: if you put your particles into a container that is fixed and you give them more energy, they're going to hit the sides of the container more than if they're not, right? And so this is that whole idea that particles that have a high temperature are going to move more. Again, these are going to be a proportional setup, right? So a sample of gas has 3 times 10 to the third millimeters of mercury inside a steel tank is cooled from 500 degrees to 0 degrees Celsius. Remember, you are going to have to convert these to Kelvin by adding 273. But if I'm cooling a gas, right, from 500 degrees Celsius to 0 degrees Celsius, I am going to anticipate that my pressure is going to go down as well because they're not going to hit the sides of the container as often. And so again, you're setting these up with pressure over temperature, and you're making sure they're paired correctly. And then you're using cross multiplication and division to solve. And as we find out, again, it's what we predicted. My pressure is less. It went from 3 times 10 to the third to 1.06 times 10 to the third. So pause the video here and see if you can get the answer. Do you get it? If I'm increasing my pressure from 15 atmospheres to 16 atmospheres, I would expect that my temperature goes up as well, right? And again, you need to make sure that those temperatures were in Kelvin. All right, last demonstration.
Today on Sci Guys, Can Crush. Welcome to Sci Guys. I'm Ryan.
I'm Adam. On today's episode, we're going to be crushing cans using air pressure.
I want to crush something.
It's supposed to be open.
Yeah, I guess you're right.
Air pressure is the amount of force that gas particles exert on their container or environment.
The equipment and ingredients you're going to need for this episode include an empty can,
A large bowl,
a set of tongs,
some water.
and a stovetop.
Because we're dealing with boiling water today, the safety equipment we're going to need include goggles, heat-resistant gloves, and an apron or lab coat to protect from spills or splashes.
The first step in our experiment is to take some cold water and fill up our bowl.
The second step of our experiment is to pour about 100 milliliters of water into the can. Turn your stove to medium-high heat and place your can with the water in it in the center of the burner. Leave it there until you see water vapor coming out of the top. Now quickly dunk your can into the water.
Today on Sci Guys,
All right, so let's talk about kind of what happened with that. Take a second, make some observations, write that on page 14 of your packet. But really, this is the only equation you need to know for any of these because all three of these variables work together. So in the can crush, you have a pressure, volume, and temperature all playing a role, right? Originally, you have this can, you have a little bit of water in it. And again, that's just to visually be able to see the vapor when you know that you have hot gas inside because gas isn't visible. And so you are heating up the gas inside the can. And while the gas is open to the surroundings, right, it's going to want to keep pressure the same. And so that gas begins to escape the container because as it heats up, the volume of the gas is going to expand and want to occupy a bigger space. And then as you take that sample of gas and you now invert it into cold water, well, you now make it a closed system, okay? Because as soon as that gas or that can hits the water, it's sealed. And so you made it a closed system, and then you are going to cool the gas inside the can to the point we know that that is going to occupy less space. It's going to hit the sides of the container less, right? And it is going, so the pressure is going to go down, the volume is going to go down because the temperature went down. Okay. And so then this is going to cause the outside pressure to be greater than the internal pressure of the can, and it's going to crush the can. Does that make sense? How all three of them kind of work together. So we can put all three of these variables into this equation. So up until this point, you had always been holding one of these three variables constant. But the reality is a lot of times all three are in play. And so here's an example of that. A sample of an ideal gas is cooled from 341 to 275 Kelvin. During this process, the volume of the gas decreases, which you would predict, right? So volume is going down. If the initial pressure was 0.75 atmosphere, what would the final pressure of the gas be? And this is the one that you can't totally predict because if a decrease of temperature, you would express pressure to be less, but simultaneously, not only are you going to be decreasing the temperature, but you're also decreasing the volume. So by decreasing the volume, you are going to hit the sides of the container more. So this is where the calculation is needed. And you set this up the same way, you just have more variables. So I have 0.75 times that liters over 341 Kelvin is equal to X or P2 times that 2.74 or 0.274 liters all over 275 Kelvin. Again, I'm going to cross multiply and divide. That's how I'm mathematically going to solve this. And I'm going to get 0.841 atmospheres. Final one, take a pause, see if you can get this. Remember, your temperatures need to be in Kelvin. Did you get it? 9.5 liters? Hopefully you did. Well, hopefully you've learned something today, and make sure that you do the rest of your packet pages. So 15 and 16 are what are for homework, and you have a concept check on Tuesday when I see you next. Have a good weekend.